Okay, so I have a question that was sent to me on TikTok, which is what is the difference between implicit and explicit differentiation? We're going to start with explicit because I think that this is probably the one that you are more comfortable with. And this is when we have an equation that can be or is already written as y equals or f of x equals. Or you might have a different variable like r or t or something, but you're probably most familiar with y. And then on the other side of the equation, you just have x's as your only variable. Okay, so y equals or f of x equals with only one variable on the other side. Okay, so an example might be something like y equals 3x squared plus 2x plus 5. This would be an explicit equation. Okay. Now, when we do the derivative of something like this, we can use our normal derivative rules to find our derivative. And our derivative in this case would be y prime equals, if we had f of x as our original equation, we're probably using f prime as our derivative. Okay. In this case, our derivative is going to be 6x. We drop this 2 down. 2 times 3 gives us 6. We reduce our exponent by 1, so we get 6x to the power of 1 plus 2. And remember, the derivative of a constant or of 5 is just 0, so we don't have anything down here for that. So if I want to write this just a little bit neater here, this would just be y prime is equal to 6x plus 2. So this would be explicit differentiation. Our original equation is y equals or f of x equals, or can be written as such. All right. And when we do our derivative, we use our normal derivative rules, and we would have our y prime equals 6x plus 2 here. Now, an important note about notation is that y prime is the same thing as saying dy dx, but we usually just use it in different contexts. And dy dx really just means little changes in y over little changes in x. It's a fancy way of basically saying rise over run of your tangent line. This is the rise. This is the run of the tangent line, which is really what y prime is, right? Y prime, your derivative is the slope of a tangent line. Rise over run is slope. So that's all dy dx is saying. Okay. Now, if we look at implicit differentiation, okay, implicit is where things get a little bit tricky. An implicit equation is one where you have essentially a give and take relationship between both x and y. So you might have something like 6xy squared plus 3y minus 2 equals x. Something like this, okay? This is an equation that is implicit. Or in other words, you have x's and y's kind of strewn about throughout the equation. This would be real tough to rewrite as y equals. Okay, so an implicit equation we can't rewrite as y equals. And you might even have other variables in here too. You might not only have 2 variables, you might be taking a derivative with respect to time. In this case, I want to take the derivative with respect to x of this whole equation. All right. So the first thing is when I take the derivative of anything that has a y term in it with respect to x, we're going to need to use chain rule. So I'm going to just show you a little example of what this is going to look like. If I take the derivative of y squared, really what I need to do is I need to take the derivative of the squared stuff, and then I need to take the derivative of the inside. If I think of having stuff squared, to do the derivative of this, I would drop the 2 down. I'd get 2 times the stuff, and then I'd have to times it by the derivative of the stuff. Right? That's what I would have to do if I was doing chain rule of something squared. I have something squared is my outside, and my stuff is the y. So when I do the derivative here, I'm going to get 2y. This is like the 2 stuff. And then I need the derivative of the stuff. And in this case, that's the derivative of y. And the derivative of y with respect to x is dy dx. So if I want to go back to this original question here and actually do this derivative, I'm going to need product rule here. So I'm going to do the derivative of x is just 1, keep my y squared, plus keep the x and do the derivative of y squared, which is 2y. But then because I'm differentiating with respect to x, I need to add this little extra dy dx. Then I'm going to do the derivative of 3y, which is going to give me 3, times the derivative of y, which is dy dx. Then I have the derivative of 2, which is 0. And then on the right-hand side, I have the derivative of x, which is just 1. Now, if I'm trying to find my derivative, I'm trying to find dy dx. So my job is to isolate dy dx. So this 0 doesn't matter to me. I've got dy dx's here and here, so I'm going to leave those, but I want to move this to the other side. So I'm going to simplify this term and give myself 12xy dy dx. Then I have 3 dy dx. Then I have 1 minus 6y squared. Now, if I want the dy dx by itself, I can take a dy dx out of both of these terms, which leaves me with 12xy plus 3 equals 1 minus 6y squared. And I'm running out of space here, so bear with me with my terrible notation. If I want the dy dx by itself, what I need to do is divide both sides by 12xy plus 3. And this is going to give me dy dx equals 1 minus 6y squared over 12xy plus 3. So you can see that our original equation, our implicit equation, had x's and y's all throughout, and I could not rewrite my equation as y equals. Our derivative of that implicit equation has x's and y's throughout. It doesn't only rely on only x or only y. All right. Now that's not always the case, because sometimes you'll have an implicit equation like x squared plus y squared equals 1 that looks up front like maybe we can't rewrite it, but we actually can. So when we do the derivative, you might not have x's and y's. You might just have one or the other. To answer the question very briefly, implicit versus explicit. Explicit is your equation can be written as y equals or f of x equals. When you do your derivative with respect to x, your left-hand side, if that's where your y was, is going to have your dy dx or your y prime already sitting there waiting for you. The implicit one has x's and y's throughout the equation. You can't rewrite it as y equals. So when you do the derivative of any term that has the variable that is not what you are finding the derivative with respect to. So here we found the derivative with respect to x. So anywhere we have a variable that is not x, we end up with an extra little term in our derivative that is dy dx. Another common one is doing something with respect to time. In that case, you're going to have dt on the bottom of your little extra funny term. So here I'd have dy dt and dx dt because there are no t's in my equation. If you want longer explanations on implicit and explicit differentiation, on my YouTube channel, I have entire playlists on both of those things. So I have a playlist for implicit differentiation and related rates. The related rates have some real world applications and situations where you would have dt with lots of examples and explanations. So if you want to see some more implicit differentiation explanations and example, please check out my YouTube channel and look for the implicit differentiation and related rates playlist.